in on offline or batch RL was actually with Emma. So somehow it feels like quite a privilege to now be talking about my research right after her. All right, so I guess each of us gave our little kind of motivation for why we're interested in this topic. And I'll give mine, which is maybe a little bit different. I'll start with something kind of perhaps a little grandiose, but I'll bring it back down to earth. So to overgeneralize grossly, if we want to ask the question, why does current modern machine learning work? At the risk of offending everyone, we could say that, well, it really comes down to two big things and then a whole lot of details. And the two big things, if you had to pick two really big things, it would be access to large data sets and the ability to train very large models, plus all the things that we as researchers actually do in our actual research. But I think it's fair to say that without large data sets and large models, we probably wouldn't see this tremendous explosion in powerful machine learning tools that are actually used in practice in domains from image recognition to machine translation to speech recognition. So to me, offline reinforcement learning is really interesting because I see it as a vehicle that could bring the benefits, the power of these large data sets and large models to the decision-making setting. So what's going on with reinforcement learning? Well, reinforcement learning is kind of in the textbook setting, like literally if you open up the Sutton and Bardo textbook, is described as an active process where you have an agent that interacts with the world, collects a sample of data, use that to improve its behavior, improve its policy or value function, and then do this all over again. And this recipe works quite well in a range of settings like playing games, board games, simple robotics tasks, etc. But if you want to take it to a setting where you have very large data sets and you want to get generalization, kind of real world, open world generalization, then in this active paradigm, what you're looking at is the possibility that you need to collect kind of ImageNet sized data sets each time you modify your policy. And that's quite impractical. If each time your, let's say, autonomous car changes policy a little bit, it needed to go back out and drive in 30 different cities in North America, that would just not be a scalable approach. And in fact, if we look at the kind of application areas where reinforcement learning has been tremendously successful and the kind of areas where supervised methods have succeeded, we see that there's a really big gulf. It's a gulf of generalization. The supervised learning methods are using large data sets and huge models to generalize across open world domains, whereas the reinforcement learning methods are doing very well in terms of control, but primarily in more narrow closed world domains. And I think this is due to the difficulty of leveraging large data sets. So can we develop data-driven RL methods that can admit large data sets? I think to get there, as we've heard from the other speakers, we need to start thinking about how to develop methods that can utilize previously collected offline data. So these are methods that are called batch RL. I'm calling them offline RL just because I think that term is a little more descriptive, but it's the same exact thing, batch RL or offline RL. And I think a more realistic formula for these kinds of algorithms, as opposed to this active online setting, would be something where you have a large data set of previous interaction data that the agent has collected, doing whatever it is it was doing, maybe from human demonstrations, maybe from its own past experience. And that large data set serves as sort of the foundation for every skill or behavior that it's going to try to acquire, in the same way that ImageNet can serve as pre-training for downstream visual perception tasks. Of course, you don't have to have a purely offline system. You could then say, well, let's go back in and collect a little more data to fix it up. But in some ways, that's kind of not the difficult part. If you can get an initial moderately competent policy from offline data, that's sort of the bit that would be the main enabling factor for a lot of what we'd like to do. And of course, this could be a path to get robotic systems that can interact with objects in the world, but I think it's also a path to get reinforcement learning to work in many other domains that traditionally have been difficult for applying RL algorithms, like the domains that Emma mentioned, things like education, medical diagnosis, scientific experimentation. There are also plenty of applications in logistics, operations research, etc., which look like decision-making problems, but are very hard to attack with reinforcement learning methods today if they require this online active interaction. All right, so in today's talk, what I'm going to discuss is why offline RL is difficult, and I'll show a few experimental results. A lot of this is going to echo some of the points raised by earlier speakers. How can we design offline RL algorithms? And then in the last portion, I'll concentrate on recent algorithm that we've developed called conservative qlearning, which seems to work fairly well in practice. Okay, so let's start with the first question. I think this is probably something that I don't really need to go into detail on for this audience, but as a quick primer for off-policy RL methods, a lot of what I'll discuss focuses on qlearning algorithms. For a qlearning algorithm, you have your usual MDP formulation with states, actions, rewards, and actions. Your goal is to maximize the expected reward of your policy, and the object that you will use to do this is the Q function, which is the expected reward that you'll get if you start in a particular state in action. And of course, the Q function has this very appealing property that if you can enforce the Bellman equation on your state and action space, then you can recover the optimal policy from that Q function. And the way we do this is by minimizing the difference between the left-hand side and right-hand side of the Bellman equation. So hopefully we're all good with that. This talk is going to focus entirely on these approximate dynamic programming qlearning methods. But of course, there are other methods for offline RL2 that have nothing to do with Q functions, which I will completely gloss over. Okay, so the high-level sketch of a off-policy qlearning algorithm, this is basically kind of the fit a Q iteration sketch, would look something like this. You collect some data set of transitions using whatever policy you want, sample a batch from that data set, minimize the difference between the left-hand side and right-hand side of the Bellman equation, and if you'd like to do so, go back out and collect more data every once in a while. And it's perhaps helpful to think of this visually as this kind of parallel process where you have your data set, you're crunching on your data set, improving your Q function, and occasionally go back out and collect more data from the world. And in offline RL, the only change we make is we skip this step. So we don't collect more data. So it might seem like, well, maybe all is good. We have this very nice off-policy framework based on Q functions. Can't we just use that to solve all of our offline RL problems? And in fact, we actually did some experiments to try to see if this could be the case, to see if essentially qlearning style algorithms could serve as the basis for an offline RL framework that's compatible with large real-world data sets. So this is an experiment we ran a couple of years ago at Google, where we developed this algorithm called qtopt. You can think of it as basically a continuous action version of qlearning. Ran a large, highly parallelized experiment with lots of robots collecting data. And then we wanted to see if data from previous experiments could be used to train up effective policies that generalize to new objects. So usually when I talk about this method, I show some videos in kind of a robotics context and talk about how it works pretty well. But what I want to talk about today actually is how this experiment informed some of our thinking about the difficulty of the offline RL problem. So the resulting system, it's an image-based grasping system. It works very well in the real world. It can pick up objects it's never seen before. But one experiment that we actually did in that paper that I often don't mention is we actually compared what happens if you take a previously collected data set from past experiments and just train up your Q function on that versus then fine-tuning it a little bit more with on-policy data collection. The amount of data available in these two regimes is pretty similar. The additional amount of online fine-tuning is less than 5% of the original data set size. But the difference in performance is actually pretty significant. So the purely offline version of this algorithm has a success rate of 87% on previously unseen novel objects. The fine-tuned one is 96%. Now you could say these are both big numbers, but if you flip them around and look at failure rates, the failure rate for the offline method is more than 3 times larger than the online fine-tuned method. So something is going on here. There's clearly a big price that we're paying from doing offline training, even in this very large data regime. And we might want to try to understand why that is. So my students, Avral Kumar and Justin Fu, ran some smaller controlled experiments to try to understand this question. We had a few hypotheses to think about. One hypothesis was, well, maybe if you just train too long with these approximate dynamic programming methods, you end up getting a kind of overfitting problem. So we tried taking an offline data set for the half cheetah task and training on that. This is with SAC, but you'd get probably the same thing with regular qlearning. SAC is an actor critic method. And we varied the data set size from 1 million all the way, from 1,000 all the way to 1 million. So blue is 1,000, red is 1 million. And you can see that there's basically no change in performance as the data set size increases. So this is not what you would expect from classic statistical overfitting. If we actually look at how well the Q function thinks it's doing, now something very strange is going on. So the y-axis here is actually a log scale. So the rewards are all kind of between -500 and 500, but for the 1,000 size data set, it thinks it's getting 10 to the 20th power in terms of its return. Now that is clearly quite a bit larger than what it's actually getting. So not only is the performance not improving with the data set size, it's also overestimating enormously by many, many orders of magnitude. Another hypothesis we had, well, maybe the training data is just not good. That's definitely not the case. If we cherry pick the best trajectories and behavior clone them, we get great results. So good data is in there and it's not overfitting. So what is it doing? Well, Tengyu's talk kind of alluded to this point already, but essentially the problem is one of distributional shift. If you solve an empirical risk minimization problem, a supervised learning problem, where you minimize the difference between f of x and y on some input distribution p of x, you could ask the question, given some new x star, is f of x star correct? What you can promise, if you're not getting overfitting, is that if you did well in terms of empirical risk minimization and you didn't overfit, then you would expect that the expected value of your error on new samples from the same distribution would be low. But you can make that same promise for samples from some other distribution. And even if you have a sample drawn from your distribution, you can make this point-wise guarantee. So the thing that you can promise is you'll be good on your training distribution. Now, you could say usually we don't worry about this because, well, we're doing deep RL, so we train giant deep nets and they just generalize because they're deep nets. That is in some cases kind of a reasonable argument, but not so in the reinforcement learning setting, because we're doing something much worse than testing our function approximator on out of distribution inputs. We're actually selecting our inputs to be the argmax of our function approximator when we're doing qlearning. And that's really bad news. So if you imagine that this is my function and this blue thing is the neural net that I fitted to this function, maybe it gets fairly low errors in most places, but if I take the argmax, I'm going to precisely pick out that peak that gets the largest error. And that's really, really bad. So where do we suffer from distributional shift in approximate dynamic programming or qlearning methods? Well, it's basically in that max. So you could rewrite the max as the expected value under some new policy. So if your new policy is just the argmax, the greedy policy, that's how you get the qlearning update. And now looking at this, you can see that in order to evaluate our target values, we need to take an expected value under some distribution pi nu, and we trained our Q function under some other distribution pi beta. Pi beta is our behavior policy, the thing that collected our data. And pi beta is not in general equal to pi nu. So if it was equal, we would expect our target values to be all good, but since it's not equal, then really all bets are off. So we expect good accuracy when pi beta is equal to pi nu, but how often does that really happen? If we're improving our policy, that's not actually the case that we're in. And even worse, we're selecting pi nu to be this argmax, which is just like the situation on the previous slide where you're actually picking out the worst errors in the positive direction. So that's really bad, and that pretty much explains why we get this massive overestimation when we try to use these methods in the offline setting. Okay, so how have people gone about addressing this issue? Well, one way that you could address it is you could limit the amount of distributional shift that you'll permit. So you could say, well, let's have some actor-critic style way of doing this. It doesn't actually have to be actor-critic. You can impose the constraint implicitly, but it's easier to think about as actor-critic, where you will update your Q function as the expected value under pi nu. But when you compute pi nu, you will constrain it to stay close to the behavior policy with some kind of divergence constraint. It could be KL divergence, it could be something else. And the idea is that if you stay close to pi beta, then distributional shift will be constrained. And this solves distributional shift, right? So you have no more erroneous values. And in fact, this kind of policy constraint style method is a fairly old idea. It goes by many different names, and it's been used in quite a number of recent papers that use it as a way to get offline RL to work better. But it does have a couple of issues. One issue, which Tengyu also alluded to, is that it might be way too conservative. The one way to think about this is, let's say pi beta is just a random policy. Then limiting the distributional shift against pi beta essentially limits how deterministic your new policy can be. It says that, well, you just have to be pretty random, otherwise the distributional shift is too large. That's often not very good. You can partially mitigate this with using a support constraint instead of a KL divergence constraint, but it's still a pretty significant issue. The second issue is that estimating the behavior policy to even enforce this constraint is itself very difficult, especially on real world data where the behavior policy might be very complicated. It might You might have data from human demonstrations or from policies that are themselves, not the result of reinforcement learning, maybe even manually designed policies. So it might be very hard to estimate pi beta. We actually did some experiments to study how hard it is. In these experiments, what we were trying to do is pre-train a policy with offline reinforcement learning and then fine-tune it with online RL. And we tested some policy constraint methods. So what you're seeing in this plot is the left side is showing offline training and the right side is showing online fine-tuning for a policy constraint method. The y-axis is the log likelihood of the estimated behavior policy. So this is not showing performance, it's actually showing how well is it estimating the behavior policy. And it does fairly well in the offline setting when given data from an easy behavior policy, but once it starts fine-tuning, it gets data from a mixture of different policies, and then the behavior policy estimate drops very precipitously, and this makes the method actually unable to improve. So that's the yellow line in this curve. And this is also corroborated in some more recent work that shows that more powerful estimators for behavior policies tend to lead to improvement across the board, suggesting that's the bottleneck for a lot of methods. One of the things you can do is you can actually avoid estimating behavior policies by using implicit constraints. So the idea here is that if you write down this constraint policy update, you can actually write down the Lagrangian of this constraint optimization problem. If you then try to write down the solution for for pi star for this constraint optimization problem, you can express it in closed form as a function of the advantage and the Lagrange multiplier lambda. This is a trick that's borrowed from some previous work. The first place where I saw it was actually a paper by Jan Peters called REPS, but I'm sure it's come up in other places as well. And it's fairly straightforward to show via duality. The nice thing about this expression is that because the optimal policy is given by pi beta times a bunch of other terms, you can approximate it via maximum likelihood with some weights. So you can optimize pi nu by maximizing an expression like this, where you take an expected value under pi beta so that it accounts for the pi beta term being multiplied into the closed form solution of log pi times the weights. And when you do this, the nice thing is that you don't need to know what pi beta is. All you need is samples from the data set. And the critic can give you the advantage. So we use this idea in a number of recent papers shown at the bottom of this slide. But one of the things that I want to talk about in the last portion of this talk is maybe all this constraint business can be avoided altogether if we can solve the overestimation problem at its root.
Okay, so just to jump in quickly, so about 3-4 minutes left.
Thank you.
Thank you.
Yeah, so that's the idea in a new algorithm that we developed called conservative qlearning. Conservative qlearning doesn't aim to directly constrain the policy to be close to the behavior policy, but instead it aims to avoid overestimation. So the problem that we saw before was that when we train from offline data, we get these out of distribution problems and we overestimate massively. So what if we can basically find these places where we're overestimating the true function and basically push down on them? So that's the idea behind conservative qlearning. The expression here shows the original kind of qlearning objective, minimizing the difference between the left-hand side and the right-hand side of the Bellman equation, with an additional regularizer that tries to find actions for which the q value is large and minimize their q value. So mu here is a distribution that's chosen adversarially to maximize q values. And this term pushes down on those q values. So it tries to specifically find these peaks and push them down, which would correct this overestimation problem. It turns out that if you have this regularizer, you can actually show that for an appropriate chosen value of alpha, q hat pi will underestimate q pi everywhere, meaning that it will provide a lower bound. Everywhere here means for all actions on the states in your data set. But the states in your data set are, of course, the only ones you use to train your policy, so that's what we want. So the algorithm is basically learn your lower bound q function for your current policy, such that it's a lower bound, and then train your policy to be the argmax for this lower bound q function and repeat. So basically actor critic with lower bound q functions. It turns out that we can actually show a better bound, a tighter bound, if we modify this objective with an additional term that also pushes up on the samples from the data. So you push down on all the samples that have high q values, and you push up on all the samples in your data set. The idea here is that if your policy perfectly matches the data, these two terms perfectly balance out and their contribution is 0. As you start overestimating, the first term becomes larger and then it gets pushed down, and that corrects the overestimation. In this case, we can no longer guarantee that you have a lower bound for all actions, but you can still guarantee that you have a lower bound in expectation for your policy, which is of course what we actually want, because we're going to use this to train our policy, to update our policy. So you're going to minimize the big Q values and maximize the Q values for the state action tuples in your data set. This is the form of the bound that we end up proving in the paper. So it has this pessimism term due to the regularizer, so this part is always positive. And then it has an error term due to essentially sampling error. So this depends on a constant that quantifies basically the concentration inequality. So long as we choose alpha to be big enough to overpower the sampling error, we'll get a bound. Okay, so does this bound hold in practice? We evaluated this experimentally. So what we're going to measure experimentally is underestimation versus overestimation. So we evaluate the expected value of our learned Q function minus the true expected value, which we evaluate with Monte Carlo samples. And we evaluated this for two variants of our method, CQL, and this CQL equation 1 is just the first version represented without that second term, which has a less tight bound. And then we have 4 different kinds of ensembles and our previous algorithm there. And what you can see is that both of the CQL methods have a negative difference, which means they're both underestimating. And the version with the second term has a tighter bound. So the bound actually does hold in practice. Whereas the prior methods generally all have pretty wild optimism. To evaluate this method, we used our newly developed benchmark suite for offline RL called D4RL, which the previous 2 talks also mentioned. D4RL has quite a variety of different tasks, including tasks that have real human data, where data doesn't just come from another RL policy, tasks that require stitching parts of trajectories. So you have a multitask data set where you have agents performing a variety of different tasks. Maybe they go from A to B and separately from B to C, and you need to stitch together those parts to figure out how to go from A to C, which is what we want from offline RL. There's more realistic tasks like driving in Carla, manipulating objects with a robotic arm, and this traffic simulator from Professor Alex Bine's group called Flow. So these tasks are meant to be a little more representative of the kind of data sets we see in the real world. If we look at the performance of CQL, so first let me present the baselines. And I'm specifically just pointing out kind of the harder tasks in the data set. In the paper, we also have the results on the more standard tasks. But the harder task is ant maze, which requires stitching, adroit, which is the 5-finger hand, and kitchen, which is that robotic arm. On a lot of these tasks, we found that a lot of previously proposed offline RL methods don't tend to work very well. A lot of them are benchmarked on data that comes from RL policies. When you have these harder data sets, it works quite a bit worse. In fact, one of the strongest baselines is simply behavior cloning your entire data set. And that's, of course, bad news. If behavior cloning your data set works better than prior offline RL methods, it means these tasks are actually pretty tough. CQL ends up doing quite a bit better across the range of these tasks, up to 5 times better on many of the hand tasks, 1.5 to 3x better when it has just the human demonstrations, 10 to 30% better than behavior cloning on the kitchen tasks, and behavior cloning is the strongest baseline on these, and essentially infinitely better on the larger ant mazes because previous methods are actually unable to get non-zero returns on these tasks. So this, in a sense, shows that those tasks are solvable because CQL can get non-zero returns. We also tested it on some Atari games using a data set from Agarwal et al., where again, we saw very substantial gains, 1.5 to 6x better. So it seems that CQL seems to work pretty well on many of these tasks. And the thing that I'm actually the most excited about is that we seem to have some idea for why it works, because it has this kind of lower bound property. Of course, there's still plenty of room for improvement. So these scores are normalized from 0 to 100, which means that in principle, future work could do quite a bit better. Okay, so to conclude, I talked about how offline RL is quite powerful and has enormous promise if we can just get it to work properly. Effective offline RL methods can be implemented by posing some constraints, perhaps implicitly, but if we can avoid these constraints and learn conservative Q functions instead, then it appears empirically like we can actually do quite a bit better. All right, thank you very much for listening, and I'd be happy to take some questions.
Thank you so much, Sergey. This is fantastic. Let's indeed open up the floor for questions. Okay, well, let me start then. This is actually a question, Sergey, that also pertains to the other talks, but I think you talked about that the most with the QTOPS results at the beginning. How much of the success of different methods is going to depend on how the data is collected? right? So with the and tasks, you're talking about this need to stitch. Maybe we can start there. Is this stitching question realistic, for example? Is that something you've seen in practical applications?
Yeah, that's a really great question. I'm glad you asked that. And I think this maybe is a good time for me to reveal a little bit of maybe a dirty secret about the QT-op results too. So I talked about how, well, we found that the online fine-tuning version did better than the offline RL version. What I didn't mention is that we actually worked pretty hard to get the offline RL version to work well. And most of what we did is alter the data collection strategy. So, one thing we found is that more randomized data collection strategies do better. And in retrospect, it's not surprising why that's the case. If you have a more randomized data collection strategy, then the support of your data is larger, which means fewer things are out of distribution. So if we were more careless about that, we would have gotten worse results for the offline setting, but probably still pretty good results for the online setting. In regard to the stitching case, I do think that's actually very realistic. And I think it's also very important because I think that's the main way that we're going to get offline RL methods that do better than the best behavior in the data set. So I think kind of the sanity check for your offline RL method, the test that it really needs to pass is if you take the best data in the data set and you run behavior cloning on that, you really should be doing much better than that. And one way that you can do much better than that is by combining parts of existing trajectories that are not by themselves optimal, but when combined together in the right way, result in more optimal behavior. And that's basically the stitching thing. So I think we have to have offline RL methods that can do that. Otherwise, they won't improve on very naive baselines.
That was a very nice talk. I had a quick question, which is for the stuff at the end when you're showing the conservative qlearning and you were demonstrating that it was in fact a much more realistic and lower bound estimate of Q. Were you using the alpha that was specified in the theory, or were you using other forms of alpha?
Yeah, good question. So this is another place where I have to admit a small dirty secret. Yes, the theory prescribes a value for alpha. I have no idea how to evaluate the theoretically prescribed alpha. So in practice, you have to select it, somewhat heuristically through some cross-validation voodoo. And I think actually an important open problem is how to figure it out automatically. I think that should be possible. We don't have a way to do that. And I'm actually really glad that you mentioned also in your talk this kind of cross-validation stuff. I think that's really one of the big outstanding challenges, not just for CQL, but for many other methods, because we always have some hyperparameters that we end up with, which we kind of have to sweep under the rug, but that's a really big deal.
I see an empty square on my Zoom. I don't know if this is a question. Lihong, you have a question.
Yeah, so if I may, so it is great talk. So in the CQL objective, the first term, you're penalizing the discrepancy from the data in a sense, right? And promoting action that are more frequently chosen. Have you thought about other alternatives that have a similar behavior and try empirically and see which one, and how they compare to each other?
Yeah, that's a good question. So as with all research projects, we experimented with a whole bunch of random stuff. And some of that stuff worked well, but we had no idea how to explain it. So we didn't write about it because we didn't understand it. So one thing that kind of seems to work is like just drive your Q values to be close to 0. So, so take Q value minus 0 squared. I think it works for much the same reason. It drives down erroneously large Q values. I think in general, there's probably a family of methods that will all have a similar effect, essentially things that drive down Q values at actions where the Q values are large. And then you have to counterbalance it with some other term that prevents just driving everything down. And for us, that's the data term. In fact, in the paper, we actually do present kind of a family of methods, and that family is defined by different objectives for mu, different objectives for the adversarial distribution. So the version that results in this kind of elegant expectation under mu minus expectation under data thing actually has an entropy regularizer on mu. You could imagine a cross entropy regularizer, you could imagine some other regularization term, and those would all yield slightly different algorithms.
I think we'll take
Cool. Thanks.
Oh, go ahead, Leon. Sorry.
Yeah, just say thanks.
I'll do them in order, in fact. So there was a question, maybe we can take 2 more questions. There was a question from Yao on the Q&A. And I think this is actually also maybe a question for the panel more generally discussion later. Are there policy gradient algorithms that could be used, Sergey, here instead of qlearning?
Yeah, there are. I'm sure Emma can say a lot more about this because she's actually done actual work on this. But yeah, in fact, many of the classic algorithms for this are policy gradient algorithms with some variant of importance sampling. And there's a lot of really fascinating analysis that we can do in terms of sample complexity and guarantees for those kinds of methods. So I completely skipped over that in my talk because I have 20 minutes and I can't cover everything. But that's a huge part of the literature.
Thank you very much, Emma. I'm looking forward to your answer maybe at 11:30. One last question, then we'll take a break, recover from Zoom fatigue a little bit. This is from Chaba, who's asking, how much does this idea of stitching rely on a Markov assumption?
Yeah, so since this is the last question, I'm going to take a little bit of time to answer properly, because I think this gets at some fairly deep issues that I just want to mention in regard to offline RL. So the short answer is yes, it does. The long answer is when you take a bunch of data that shows behaviors with different levels of optimality, different returns, and you're asking to do better than the best thing in the data set, there must be some structure that you can exploit. If there's no structure, then the best you can do is just pick the max. So what is the structure that we exploit in offline RL? Well, it's the temporal structure. In fact, if we make no further assumption, the temporal structure is kind of all we've got. So we need to have some kind of structure, which means that we need to have the Markov property to hope to do better than the best thing in the data set. If you have observations, if you're in a PUMDP setting, well, go and learn your state space so that you do have the Markov property, and then you can do better.
That makes sense. Well, thank you very much, Sergey. Thank you all for this first three talks and accommodating the virtual schedule. This is a phenomenal start to a workshop which promises great things. So on this note, we're going to take a half-hour break to be back at, struggling with time zones here, to be back at 1:30 Eastern time or 10:30 Pacific time for one more talk. No, I'm getting this wrong. You're right. We're going to be back at 2 p.m. Eastern time and 11 Pacific time. And for one more talk by Ophir Nahum, and then we will have a discussion at 11:30. So thank you all for this, the morning talks, and I'll see you in half an hour.